everybody. Today it's Science Friday 46, and I asked my dad a question.
So let's get down to it. All right, everybody, welcome back to Science Friday number 46. Once again, I have my son MJ with me, which means this also won't be behind a paywall so that anybody can look at this. This week, MJ, again, he goes to a really good school. They have a good science program, a place called Gen Prep here in Pocatello. And he has some questions about science. So what was your question this week, buddy?
I said, is the center of the Earth hot?
And the center of the Earth is, in fact, extremely hot. In fact, what did I tell you the center of the Earth was hotter than?
Hotter than the surface of the sun.
That's exactly right. The center of the Earth is, in fact, hotter than the surface of the sun, even though it's a solid. We're going to get into that as we go along today. So let's talk about the interior of the Earth and how it's structured, what it's made out of, and kind of what it does for us, because the inner portion of the Earth really affects what's going on the outside of the Earth. So the first thing that you need to know is that the inside of the Earth is very active. The Earth is heated very vigorously from below, principally by the radioactive decay of elements. Now, some of the heat left over the interior of the Earth is what's called in situ heat. It's left over from when the Earth was originally very, very hot everywhere and mostly molten. Some of that heat gets trapped on the inside. The insulating layers are pretty good, but most of the heat is generated by the radioactive decay of heavy elements that are found deep inside of the Earth. Because the center of the Earth is hot, the Earth is very active. That's why we have continental drift. That's why we have earthquakes. All that stuff is due to the fact that the center of the Earth is quite active. So, also, the Earth has a magnetic field, a kind of an interesting magnetic field because of things that go on in the interior of the Earth. So, what does the interior of the Earth look like, and how do we know what it looks like? I mean, nobody's ever dug a hole deep enough to really probe very far below the crust of the Earth, which is the outermost layer in the part of the Earth that we live on. Well, the reason we know what's on the interior of the Earth is sound waves, seismology. Basically, anytime anything shakes on the surface or in the interior of the Earth, it sends sound waves or seismic waves throughout the Earth. And this isn't about seismology, but there's basically two types of waves, S and P waves, and they behave roughly as longitudinal and transverse waves. And they behave differently when they interact with different boundaries between solids and liquids, for instance. And their refractory properties and their reflective properties are slightly different depending upon what they're seeing. And by putting together lots and lots of seismographic data, you can get a pretty good impression of what's going on in the inside of the Earth. And as seismology's gotten better, the resolution of those images has gotten better. So there is still some mystery about what's in the center of the Earth when it gets down to some of the finer points, but the general picture looks something like this. The Earth has basically four layers. There is a solid outer crust. There is a mantle underneath that solid outer crust, and the mantle is sort of plastically overall. It's not a complete solid. It's not a complete liquid. Underneath that, there's a liquid outer core, and beneath that, there's a solid inner core. So there's four layers, four interior layers to the Earth. So let's talk about what those layers look like. The crust, the outer layer, the layer that we live on, is less than 1% of the Earth's mass, and it's composed basically of two different types of crust. There's a continental crust and there's an oceanic crust. The continental crust is mostly granitic in nature. Now there's some sedimentary rocks and some metamorphic rocks and other things, but overall, continental crust is made of granitic types of rocks. It's an igneous type of rock, but it's a not very dense igneous type of rock. The oceanic crust on the ocean floors is more basaltic because it comes up from the mantle, from underneath, through spreading centers in the ocean. It's a much more dense rock. Basalt is denser than granite. Now, you go down into the upper part of the mantle. The upper part of the mantle is also solid. And the crust of the upper part of that mantle are known as the lithosphere. As you go down into the mantle, though, properties start to change a little bit, and it goes from being sort of solid to more of a plastic type of material. And there's actually convection in the mantle, just like convection in a pot of boiling water on the stove. And that convection in the mantle is what drives continental drift. It's what causes mid-ocean spreading centers, where magma comes up from deep inside of the earth and it sort of spreads out along the seafloor. It's what causes continents, which float on top of the mantle, to move around. That's one of the things, that motion in the mantle, that convective motion, is responsible for plate tectonics, earthquakes, an awful lot of volcanology. You get subduction zones where the ocean tries to slide. Because the ocean crust is denser than the continental crust, when they meet, the ocean crust will generally subduct or try to move underneath the continental crust. There's a lot of friction that's created there, and that creates volcanism. That's what the Pacific coast, the Pacific Northwest volcanoes are all about. There's a subduction zone there. So the mantle, even though it's buried down there a pretty good ways, actually has quite a bit to do with things that occur on the surface of the earth. Now, underneath the upper mantle, you get into something known as the asthenosphere. And the asthenosphere is the part of the mantle that's kind of more plasticky. The mantle, by the way, is about 68% of the earth by mass. The remaining parts, the liquid outer core and the solid inner core, are about 31% of the earth by mass. Now, the liquid outer core and the solid inner core are made out of mostly iron and nickel. There's some other things in there too, and there's some important elemental differences, but mainly they're both nickel and iron. The big difference is the outer core is liquid, the inner core is solid. And we know that because of the way the S and P waves interact when they cross those boundaries. Now, the outer core is really hot because it's being heated very vigorously from below by the inner core. But when you get to that inner core, as soon as you enter the surface of the inner core, the temperature really jumps up. It's around 6,000 Kelvin, around 800 degrees Fahrenheit, and that's hotter than the surface of the sun. So the surface of the sun's around 5,800 K. And so the center of the earth really is hotter than the surface of the sun. And again, this is due to radioactive decay and the remnants of some in situ heat. So what does this have to do with the Earth's magnetic field? That's another great question. Well, the Earth's magnetic field is created in the liquid outer core of the Earth. Magnetic fields are due to charges in motion. That's a simple answer. So if I have a charged particle and it travels along some sort of a path, it creates a magnetic field. And typically these tend to form closed loops called current loops. That's why anytime if you have a wire and you energize it, you can measure a magnetic field that springs up as current flows through the wire. Well, inside of the liquid outer core, there are charged particles. They're charged because they're very, very hot. They're ionized, and they're moving around in current loops. And each of these little current loops produces a tiny magnetic field, and the addition of all of these individual little current loops produces a pretty robust, whopping magnetic field. Now, the inside of the Earth, that big solid slug of nickel and iron right at the center of the Earth, you would think that would be a big ferromagnet, especially since iron is the quintessential ferromagnetic material. Well, it turns out it doesn't work that way because it's too hot. It's above something known as the Curie temperature. Above the Curie temperature, those little individual magnetic domains that are created by individual little particle loops of things like electrons orbiting atoms, they don't align anymore because the Curie temperature is high enough that those particles are energetic enough that the little magnetic domains just won't align all by themselves. But because of the magnetic field created by that liquid outer core, it forces all those little domains that are inside of the solid inner core, albeit above the Curie temperature where they're basically pointing in all kinds of random directions. It forces them to align with that big, strong external magnetic field. And that ends up boosting the magnetic field strength. You just add it vectorially, and you get a pretty whopping magnetic field. It's called a geodynamo effect, and it's basically like an electrical generator, a few twists and turns aside. So the Earth ends up having this great big whopping magnetic field due to the electrodynamo effect. Again, there's a lot of convection, lots of current loops moving around in that liquid outer core. It produces a big magnetic field. That magnetic field then penetrates the solid inner core, forces those misaligned little magnetic domains, and they're misaligned due to the fact that the Curie temperature is too high to line up. You get to add all those magnetic fields together, you get a great big whopping magnetic field. That turns out to be quite a benefit to us. If you look around at the other inner rocky planets in our solar system, the Earth is the only one that really has very much of a magnetic field. Mercury, virtually none. Venus, virtually none. And Mars, virtually none. Now, which is the only one of those planets that's habitable? It's Earth, and that's not by accident. You would think that Mars could be habitable. Well, one of the reasons that Mars isn't habitable is because the atmosphere is too thin. There's a robust sort of a greenhouse effect that occurs on Mars that keeps the atmosphere as warm as it is due to the presence of a lot of carbon dioxide in the Martian atmosphere. But at one time, liquid water obviously flowed on the surface of Mars. Mars had a much more robust atmosphere, and it's thought now that it wasn't some catastrophe that removed the Martian atmosphere. It was the fact that Mars has never had very much of a geodynamo. The rotation's fast enough, but it doesn't have the interior structure that you need to really ramp up a big effective geodynamo, so it doesn't have very much of a magnetic field. And because it didn't have very much of a magnetic field, over the eons, the solar wind slowly eroded the Martian atmosphere until there wasn't enough of it left to keep the pressure and the temperatures high enough that it could maintain liquid water on the surface. That's probably what happened to the liquid water on Mars. Now, if you go to the other side of the asteroid belt and you get into the outer planets, Jupiter has a magnetic field that rivals that of the Sun. It's really big. All of those outer gas giants have magnetic fields associated with them one way or the other. And the magnetic field of the Sun actually influences things that are on Earth. The Sun creates a magnetic field in a slightly different way than the Earth does. It's a geodynamo, but it works just a little bit differently. And we'll talk about that on another Science Friday. So, to recap, buddy, what did you learn? What are the layers of the Earth from the outside in?
There's the crust, the mantle, the liquid outer core, and the solid inner core.
That's very good. So, which layer do we live on?
The crust.
That's very good. And what two layers are responsible for creating the magnetic field? Is it the liquid outer core, maybe, and the solid inner core?
Yeah.
Does that sound right?
Yeah.
Okay. And is a magnetic field a good thing?
Yeah.
Yeah, it basically keeps our atmosphere intact, kind of shields us from the solar wind a little bit. And then one last thing, let's get back to the original question that you asked. Is the interior of the Earth hot?
Yeah.
It's real hot. So as you dig down, it doesn't get colder, it gets hotter, right?
Yeah.
Into the Earth. And that's because of the decay of radioactive materials. So if you go way down in a deep mine, would you expect it to get hotter as you go down or colder?
Probably a little cold when you go down, but then it'll get hotter.
Yeah, that's actually really good. It does get cold for a while, but as you get really deep into a mine, it actually heats up. And really deep diamond mines that they find in things called peridotite dikes, they're actually quite hot. They have to have air conditioning down there because without the air conditioning, the temperatures would be over 140, in some cases 150 degrees. It's because the deeper you go into the Earth, the hotter that it gets. And finally, how hot is the very center of the Earth? What would you compare it to? If you wanted to compare it to something else in the solar system, what would you compare it to? It's about as hot as what?
The center of the sun?
Yeah, the sun, not the center of the sun, the surface of the sun.
Okay.
So anyway, that's it for this week. Again, no paywall this week. And we'll figure out something else to talk about next week. As long as he keeps having questions, I'm going to do these without a paywall. So that's it for this week. I'll be seeing you. Can you say cheers?
Cheers!